All right, in this section, we're going to be covering limits involving infinity, which means the answer to a limit can be positive or negative infinity, or we can have x approaching positive or negative infinity when we evaluate a limit. So first, we're going to talk about when answers to a limit can be positive or negative infinity. So a lot of the time, technically not all the time, but a lot of the time when this happens, when you get an answer to a limit where the answer is positive or negative infinity, is when we have a vertical asymptote, when x is approaching a. So when we have vertical asymptotes, and if we have x approaching a, where a is the vertical asymptote, that can lead us to these several examples right here. Either we might have an asymptote where the function's going to infinity on both sides, going to negative infinity on both sides, or positive infinity on one side, and negative infinity on the other. So taking a look at the first graph over here on the left, as we approach a from the left and the right, both sides are going to infinity, which means the limit in general exists and it also equals infinity. Technically speaking, sometimes you can also write D and E if the answer is positive or negative infinity. I prefer writing positive or negative infinity though. So that's an example of all three of those equaling infinity. Same idea for the next one. As we approach a from the left and from the right, the one-sided limits are both negative infinity. Since they're the same, the limit in general is also negative infinity. For the next one, you can see that as we approach it from the left side, that's going to be going to infinity. As we approach it from the right side, that's going to negative infinity. And then since the limit from the left goes to infinity, the limit from the right goes to negative infinity. Since those are not the same, the limit in general does not exist. Same idea for the last one. We have the limit from the left going to negative infinity, the limit from the right going to positive infinity, which means the limit in general does not exist since the one-sided limits are not the same. So let's go ahead and see an example where we actually have a function with some numbers here. So let's say we want to find the limit as x approaches 2 from the left and the limit as x approaches 2 from the right for this function that's given to us. So if the graph was not given to us, let's say this graph was not given to us and we only had the function, this is an example of one where if you try to do direct substitution and you plugged in 2, you would get 1 over 0. Notice this is not the same as 0 over 0, right? We talked about 0 over 0 last section, I believe. 0 over 0 is indeterminate form. There's different techniques we can use for that. If you get another number other than 0 over 0, that usually will mean there's a vertical asymptote, which means your answer will be positive or negative infinity. So you can actually make a table for yourself and plug in values getting closer and closer to see if your answers are getting closer to positive or negative infinity. But we're primarily going to deal with questions that are given graphs for these types of questions. So let's go ahead and use the graph. Limit as x approaches 2 from the left. So here's 2. Of course, that's where the vertical asymptote is. As we approach it from the left-hand side, it looks like the curve is going down to negative infinity, right? So as we approach 2 from the left, the function is going to negative infinity. Let's do the limit as x approaches 2 from the right. So as we approach 2 from the right-hand side, it looks like it's going up to infinity. So it's going all the way up, arrow going up, means the y values are going to infinity. So a lot easier when we have the graph in front of us so we don't have to make a little table. First, we don't have to recognize that it's 1 over 0 after direct substitution. So we don't have to make a little table for ourselves. We can just look right at the graph. A lot easier for these types of questions. Okay, the next one that we might see is when x is approaching positive or negative infinity. And this is when, once again, it doesn't have to be regarding an asymptote, but a lot of the time it is. So usually when we see these questions, we're dealing with horizontal asymptotes. So a lot of the time when our answer is positive or negative infinity, we're dealing with vertical asymptotes, a lot of the time when x is approaching positive or negative infinity, we're dealing with horizontal asymptotes. Once again though, not always, but that's primarily what we'll be focusing on. So you might see the same notation that we've been using before, except notice that x is approaching positive or negative infinity. So when you're looking at this on a graph, because infinity is not a number, right? Positive and negative infinity is not a number. So when you're looking at this on a graph, x approaching positive infinity means x is getting larger and larger, which means you're going to look all the way to the right on the graph and see where the y values are going. X approaching negative infinity means x is getting more and more negative, which means you're going to look all the way to the left on the graph. All right, so let's go ahead and see an example. Once again, we're gonna have this where we're given a graph. We're gonna see other ones where we don't have a graph and how to handle them. But let's say we want to evaluate the limit as x approaches negative infinity of g of x. A nice little hint for these is if you're not given the graph, maybe you can actually graph it pretty quickly. Technically, we should be able to graph 1 plus e to the x because you can graph the exponential function e to the x, and then plus 1 is a vertical shift up 1 unit, which means instead of the horizontal asymptote being on the x-axis, the horizontal asymptote gets bumped up to y equals 1. Either way, this one we are given the graph, and we want to know what is the limit as x approaches negative infinity. So negative infinity means we're going all the way to the leftmost point on the graph and see what's going on. There should be an arrow. So since there is an arrow going all the way to the left, and since there is a horizontal asymptote, that means the function is getting closer and closer to the horizontal asymptote, and the horizontal asymptote is a value of 1. So as x approaches negative infinity, the more and more we go to the left on the graph, the y values are getting closer and closer to this horizontal asymptote, which is a y value of 1. Okay, let's see one more of these. And this one looks really messy, right? If we were not given the graph, we have this kind of nasty looking function, and we want the limit as x approaches infinity of this nasty looking function. But once again, we don't even care what the function is when the graph is given to us, because we can just look right at the graph. So looking at the graph, we want to know what is the limit as x approaches infinity. So positive infinity means we're going to look all the way to the right and say, where are the y values approaching as x gets larger and larger, more and more to the right. So once again, just like the previous one, it looks like as we go more and more to the right, it's approaching this horizontal asymptote, which is a y value of 2. And then you're done. So x approaching positive or negative infinity, usually we're dealing with horizontal asymptotes where the horizontal asymptote will end up being the answer. Technically, it doesn't have to be, but it usually is. But we'll see examples of ones in a second where it's not a horizontal asymptote. Okay, so now we're going to be doing the rest of these questions in the last few pages here, where they're a little bit harder because now we're not going to be given a graph, and we're going to have to go over these certain techniques that allow us to evaluate limits as x approaches positive or negative infinity by hand. So we're primarily going to be dealing with rational functions here, which is going to make this a little bit easier. So in general, these little rules that you should know, that you need to know for doing these questions, is if your function is for x to a positive number, so like 1 over x squared, 1 over x to the point 2, 1 over x to the fifth or something, and x is approaching positive or negative infinity, this is always going to be 0. Technically, the number doesn't have to be 1. This could be any number. It doesn't have to be 1 in the numerator. It could be any number, and it's still going to be 0. So if you think about why this is, let's just see this example. So this example right here, the limit as x approaches infinity of 1 over x squared. So based on this definition, since 2 is a positive number, then we know the limit as x approaches infinity of 1 over x squared is just going to be 0. So piece of cake, right? As long as you remember this, that is a piece of cake. The reason why this is, if you always try to think about these questions logically, x goes to x approaching infinity. That means x is getting larger and larger. If you are plugging in values to 1 over x squared, where x is getting larger and larger, x squared is getting larger and larger. If the denominator is getting larger, the number as a whole is getting smaller and approaching 0. For example, if we made a really quick XY table here, and let's say we chose some X values like 10, 100, 1,000, 10,000, and you could keep on going if you wanted to. And then you take these values one at a time and you plug these into your function. If you plug in 10, you would end up getting 1 over 10 squared, which is 1 over 100, which is already pretty small. That's 0.01. If you plug in 100, you would get 1 over 10,000, which is really, really small. If you plug in 1,000, you would get 1 over 1 million. And then lastly, if you plug in 10,000, you would get 1 over, 100 million. So long story short, as x gets larger and larger, the y values are getting smaller and smaller, which means they're getting closer and closer to 0. Hopefully, we don't have to do a table for this. You shouldn't have to. Just know this as a nice little shortcut. All right, so here is the deal for how we do these when they get more complicated. So this technique is only when x is approaching positive or negative infinity. Right? We typically try direct substitution when x is approaching a number. All right, so if we have a rational function, which we do, 5x squared minus 7x plus 1 over 2x squared plus x plus 5, rational function, and x is approaching positive or negative infinity, what we're going to do is we're going to divide the numerator and denominator by the largest power from the denominator. So from the denominator, the largest exponent is x squared. So we're going to divide the numerator and denominator by x squared, and then let's just see what happens. So when we do this, we divide every single term by x squared. Essentially, you're distributing the 1 over x squared to every single term. So try to do this in your head. 5x squared divided by x squared is just 5, right? The x squareds cancel. And then we have 7x divided by x squared. X divided by x squared is 1 over x. So it's just 7 over x. And then 1 over x squared is just, nothing simplifies, it's just 1 over x squared. So now we're going to do the same thing to the denominator. 2x squared divided by x squared is 2 because the x squareds cancel. X divided by x squared is 1 over x. And then lastly, 5 over x squared is just 5 over x squared because nothing cancels. So we divided every single term from the numerator and denominator by x squared. Now what we're going to do here is technically we're using limit laws, and we're going to do the limit of the numerator and the limit of the denominator separately, which means we're going to do the limit of every single term separately using limit laws again. So I'm going to write this out just so we can see what's going on behind the scenes, but we don't have to actually write it out like this every single time. So it's the limit of the numerator divided by the limit of the denominator, and then it's going to be the limit of each one of those terms individually. So the limit of each one of these terms individually, and that looks awful, right? Limit of x approaching infinity everywhere. You could go one step further. Once again, you don't have to do this. I'm not even going to bother writing it out again. But if there's a constant, you can write the constant out front because it's not dependent on x. It's not dependent on the limit. And you could actually write that as 7 times the limit as x approaches infinity of 1 over x. just to kind of make it the limit look a little bit easier, but you don't have to. So long story short, there's going to be a shortcut that we can use that we're going to use in about 1 second here. But now we're going to do each one of these limits separately. So we know that the limit as x approaches infinity of 5 is just 5, right? It's a constant. We also know, based on what we just saw a second ago, the limit as x approaches infinity of a number over x is 0. So that's going to be this rule right up here. Same rule right up here that we just did a second ago. That is 0. Same idea for the next one. As x approaches infinity, 1 over x squared is going to approach 0. For the denominator, that's a constant, so we're just left with 2, just the constant. And then the limit as x approaches infinity of 1 over x is also 0. As x approaches infinity of 5 over x squared is also 0. So the shortcut, just like that we saw above on this page, is if as long as x is approaching positive or negative infinity, and the function is a number over x to a positive exponent, it's always going to approach 0, which is great because then we're done. 5 minus 0 plus 0 over 2 plus 0 plus 0. We're left with 5 over 2 as the answer. So let's see one more page of this, but we're not going to go through. We'll do this pretty quickly. We're not going to rewrite these last two annoying steps. We're basically going to write this part, and then we'll get the answer right away. All right, so there's 3 things that could happen. If you think back to rational functions, let's go back to this one real quick. This number is actually the horizontal asymptote for this rational function. You compare the degree of the numerator with the degree of the denominator. Since they're equal, the horizontal asymptote is the ratio of the leading coefficients, which is y equals 5 over 2. So honestly, what we're doing here is we are finding the horizontal asymptote for a rational function, but we're doing it using limits, and we're doing it by showing our work instead of using the rational function shortcut. All right, so let's take a look at these 3 outcomes. Either the denominator is larger, the numerator is larger, or they are equal in regards to the exponents. So let's do this first one. So we have the limit as x approaches infinity of 2x cubed minus x over 5x plus x to the 5th. So the denominator's exponent is larger, right? 5 is larger than 3. We're going to start this off the same way. We're going to divide the numerator and denominator by the largest exponent from the denominator, which is x to the 5th. Once again, we only do this when x is approaching positive or negative infinity. So we end up getting the limit as x approaches infinity. Let's do this in our head. 2x cubed divided by x to the 5th is 2 over x squared. And then we have x minus x over x to the 5th is 1 over x to the 4th. And that's all divided by, we have 5x divided by x to the 5th, which is 5 over x to the 4th, plus x to the 5th divided by x to the 5th, which is 1, because they cancel completely. And now, instead of using those limit laws and annoyingly write it a million times, the limit a million times, now you can just do each term individually. So now you're just going to do the limit of this and then the limit of this individually. So since the limit of, as x approaches infinity, of 2 over x squared is a number over x to a positive number, that's going to approach 0. Same thing with the next one, that will also approach 0. Same thing with 5 over x to the 4th, that'll be 0. All we're left with in the denominator is 1. So we're left with 0 over 1, which simplifies to 0. So remember, when this happened with rational functions, the denominator's degree was larger. That meant there was a horizontal asymptote at y equals 0. But now we're just showing our work for it using limits. So if a question said you had to show your work, you would have to do it this way instead of using this shortcut. All right, next one. We have the degree of the denominator is larger. So you might remember if the numerator is larger, that means there is no horizontal asymptote for a rational function. Also notice numerator is 3, denominator is 2 for the degree. Limit as x approaches negative infinity. So we're going to divide the numerator and denominator by the highest degree from the denominator every single time. And I'll do this one a little bit quicker. Divide every single term in the numerator by x squared. You would get 1 over x plus 4x. And then divide every term from the denominator by x squared. You would get 1 plus 2 over x minus 1 over x squared. And now every term individually, you're going to evaluate the limit. Any one of these that has an x in the denominator essentially is going to approach 0. So 1 over x will approach 0 as x approaches negative infinity. 4x does not approach 0. That is not in the denominator, it's in the numerator. So we'll come back to that in a second. 1 is just 1. 2 over x approaches 0. 1 over x squared approaches 0. So what we're left with here is 4x over 1, right? Which is just 4x. So now all we're doing here is trying to evaluate the limit as x approaches negative infinity of 4x. Couple different ways you can do these ones. You should not do direct substitution. The reason you should not do direct substitution is because infinity is not a number. So don't actually plug it in. Just kind of ask yourself, as x goes to negative infinity, where is 4x going to go? So even though I just said don't do it, in your head, you could write it down, but just cross it off like I'm going to do afterwards. If you plug in negative infinity, once again, really bad notation that really doesn't make any sense, but if you plug it in, 4 times negative infinity is still negative infinity, right? There's positive times a negative, so it's still negative. So this is going to be negative infinity. So don't actually write that down. If you do write it down, just delete it. Just ask yourself, as x gets more and more negative, what's going to happen to 4 times x? That's still going to get more and more negative. You can and should always try to think of things as graphs as well. So you could imagine y equals 4x. This function y equals 4x is a linear function. Y-intercept of 0, slope of 4. So basically, as x approaches negative infinity, the more we go to the left, the further down the function is going to y values of negative infinity as well. So when you do limits, if you can imagine the graph or even draw it out, draw out the graph of the function, evaluating the limits is actually going to be a lot easier. So basically, so far here, if the denominator is larger, the answer is going to be 0. Once again, you should show your work though. If the numerator is larger, there's not going to be a horizontal asymptote, but the answer will be positive infinity or negative infinity. You would have to figure that out on your own. And then last one, if the degrees are equal, like we saw a second ago, we know the answer is going to be the ratio of the leading coefficients. But let's go ahead and actually do this question. Always keep in mind, I know I said this a couple times, these techniques are only true when x is approaching positive or negative infinity. So we divide the numerator and denominator by the highest degree from the denominator. So if you're wondering why we do it from the denominator and not the numerator, I recommend, it wouldn't change in this case, but maybe try to go back over here and divide everything by by x cubed and see what happens. You'll see why we use the denominator. So divide everything by x cubed, we would end up getting 4 minus 3 over x squared minus 5 over x cubed in the numerator. Divide everything by x cubed in the denominator, we're left with 5 plus 1 over x. And then we use the shortcut. Any term with an x left over in the denominator will approach 0 as x approaches positive or negative infinity. And then all we're left with is 4 over 5. And then we're done. So just like we said a second ago, the answer is going to be the ratio of the leading coefficients. Once again, though, you need to be able to show your work because we're actually evaluating this using limits. So in your head, you know the answer should be 4 over 5. So it is a good way to check your answers. All right, so that is it for this section.